Hey guys, in this video I'll be talking about how to construct and code a 5x5x5 LED cube. If you haven't watched the demo yet, check it out from the link in the description. Now let's get started. The LED cube is made up of a total number of 125 LEDs organized as 5 layers, with each layer containing 25 LEDs arranged as a 5x5 grid. All the cathode pins of all the LEDs in this grid are connected together. One such layer is shown in the schematic, and this is how each layer was constructed. Along with this, the anode pins in each layer are connected column-wise and then terminated by a current limiting resistor of value 220 ohms, which will then ultimately connect to our Arduino Nano I/O. The main motivation behind this grid formation is to reduce the number of I/O required to control the entire cube. We can now control 125 LEDs using just 30 pins, but Nano offers way less I/O than the required number. So the solution is to use a serial in, parallel out shift register. Here we use the 74HC595N, which increases the I/O count by 8 pins. So daisy chaining 4 shift registers can increase our total I/O count to 32 pins, enough to control the entire cube. And the best part is, to control these 4 shift registers, we just need 3 pins from the Nano. There's another problem. If we consider that each LED draws around 20 milliamps, and if you turn on every anode column and every cathode layer, we will draw huge amounts of current, posing a threat to our power supply as well as the switching transistors. To avoid this, we can just run one layer at a time. This is called as multiplexing. But what if you need 2 or more layers to be active for a particular pattern or an animation to render on the cube? Let's take a look at this video for the solution. Here, the LED cube is programmed to turn on each layer on and then turn off and move on to the next layer. And there is a small delay between this operation. And progressively, this delay gets smaller and smaller. At one point, it seems to the eye that all the layers are active at the same time. This is because of an illusionary effect known as persistence of vision. We will catalyze on this effect to render any given animation by keeping just one layer active at a time. Let's dig deep into the code to see how this is done. I will start by briefing about the variable and function which is used to hold and transfer the data into the shift register on the circuit. One such variable is this shift_reg 32-bit integer array of length 5. Each index holds the 32-bit value for each layer of the cube. One more function to look out for is the shift25 function. This function breaks the 32-bit input value given to it into 4 1-byte or 8-bit chunks, and then these chunks are pushed out one by one using the SPI protocol. To achieve multiplexing, we can set up a software interrupt to load each layer at a specific interval. More details about the timers and interrupts is given in the description. To briefly explain what timers are, they are just like alarm clocks. You set up an alarm at a specific time, and when this alarm hits, a piece of code executes, and this goes on and on. And this ISR is that piece of code. Here I'm calling the shift25 function for each layer by using a layer count of mod 5. Since the interrupt time that I have set for this project is around 260 microseconds, persistence of vision comes into play and you don't see that jitteriness when the cube is rendered. But how do you know which is the right value to be loaded into the shift reg to get a particular pattern or to make an animation? For that, I have made this Python script. Running it will greet you with a GUI showing a 5x5 grid, which can be interpreted in 2 ways, either as the last layer from the top view or the backmost layer from the front view. So let's see an example from the front view. Imagine if you want to generate this random pattern. So you can go ahead and click these LEDs along with me, and you will be greeted by this hex code on the right hand side, and these numbers are the shift reg indexes. So putting this hex code in the 0th index of the shift reg will generate this pattern at the lowermost layer. So what I'm going to do is I'm going to copy this and I'm going to go into the Arduino code, and now I'm going to paste that hex code in the 4th layer, and now I'm going to save and run this, and this will be the output. So let's see an example for the front view now. So you can just reset and hit the front view, and then now let's generate the number 1. So I'll click the appropriate LEDs and I'll get the required value. Now I'll copy this value into the Arduino code. One thing you have to remember is running this code just as it is now will render that number 1 at the backmost face. So to bring it front, you could just do a left shift followed by 20. So this will bring it to the frontmost face. So I'll do it for all regs, and now I'll run the code, and this will be the output. To make a moving animation like a sine wave, you could just break the entire animation into frames, and then you can load those frames in the Python program and you can get the appropriate hex values. I have stored all these hex values in an array and I'm calling it one by one with a small delay, and that gives me this animation. This is how you can generate your own custom animation. I have followed this method to render animations in my program like the cube border, helicopter, the faces, and the sine wave, and also mainly the alphanumeric display. You can instead use general math functions to plot the patterns using the pixel set utility given in the program. I've used such an approach to render the 3D sine wave. Lastly, I want to share something interesting with you. Since we are performing such high frequency switching, isolating these surges from the nano is quite important. Let me show you why. Here, I've loaded a program into the cube to cycle between a 5-second on state and 1-second off state for the entire cube. But that doesn't happen, but rather the nano glitches out. Now, if I add a 10 microfarad in parallel with the existing 0.1 microfarad, it works properly. And again it glitches if I remove it. The reason is the lower the capacitor value, higher the cutoff frequency. Adding the 10 microfarad keeps the decoupling frequency low enough to prevent the on and off surges from entering the nano, and that's why decoupling caps are mandatory for this project. That's it guys. Thanks for watching. If you have any question, post it down in the comments, and don't forget to subscribe. Until next time.